Hello and welcome. In this video, we're building a complete LS-DYNA crash model from scratch using LS-PrePost. The plan, the keyword file from top to bottom is first the control, how long the simulation runs and how it marches through time. Second, the database, what our results should be, we need to get written to the disk, because if you don't ask, you get nothing. Then we have the parts, which ties together the geometry and the cross section and the material for the material card. And fifth, the mesh and nodes and elements. Sixth, the contact, so that the tube doesn't pass its earth as it falls. Seventh, we have the loading, the rigid wall that drives the crush. And eighth, we have the boundary condition. This is the model here, so that you can imagine we're talking about. It's just a square steel tube with a cross section 50 millimeters by 50 millimeters, and the length is 200 millimeters. And as you can see, the rigid wall travels down along the -z axis at a velocity of 10 millimeters per millisecond. This slide here is very important slide, the unit slide, because as you know, LS-DYNA is an unitless, and it doesn't know whether your numbers are meters or millimeters, seconds or milliseconds. It simply does arithmetic. Whatever you type, that means the responsibility for consistent unit system is entirely yours. So here we're using the most used unit system for crashing, which is millimeters, kilograms, and milliseconds. First, we're going to start with the control card, starting with first adding the title to our model, then the termination, which is the length of the simulation. Let's start first showing you in LS-PrePost. First, I'm gonna just create the geometry so that you can imagine and see or visualize what we're trying to do. I'm using a very simple method of creating first the geometry, solid geometry. Then I'm gonna mesh the surfaces of this of this box to get the tube we want. This is there are a lot of other ways to do that, but I'm just using a straightforward method. After selecting the surfaces of the box, I'm gonna just write down the element size, then mesh it. I ignored on purpose here our final step. If we're going to use this method, I just ignored it because I want to show you when we do the running what will happen. So we'll come back to it later on. Then, as I said, we start. Of course, we're gonna save it first, then save, and then we will open the control cards. But first, we're gonna open the title keyword title card to add a title for the file we have, because if you have lots of models in the future or lots of files, you're gonna need to know which is which. So it's a code habit to learn early on. So let's type crash tube impacted by moving wall, accept, and done. Then we go to the control and then scroll down to termination. Oh, here it is. Right. So the first field, which is the end time, it's the end time, and we set it to 6, which means in simulation stops at 6 milliseconds, which would be about 1/3 of the crash box, because after 6 milliseconds that would be about 30% of our 200 millimeters tube. Then I choose control the energy. When I choose 2 here, to set the energy calculations on. And then I'll scroll to control our glass, and we'll type the value of 4 and QH coefficient to 0. Type 4 is stiffness based control that resists it well in crash problems. Okay. Then for the database, we have to specify what output we would like. So we'll head now to the LS-PrePost and scroll to database, and First, we will specify the database binary D3 plot. And we'll add 0.2 and then we'll go to the ASCII options to add the other outputs we want. Taking a bit of time to open. Here it is. So we will. I like to add binary. It's an additional. The binary is an additional file for to visualize the final output. GLStat 0.1. It's a bit finer than the D3 plot because 0.2 will give me about 30 frames for the simulation. So when I type here for the timing or the internal timing would be 0.1 to get a bit of smooth curves, smooth results, a bit finer than the D3 plot. Then done. It's taking a bit of time loading here. Here I'm just gonna modify it to make it a bit more finer. Let's make it 0.05 to make the results more finer than the D3 plot, to get smooth curves. The thing is, the D3 plot files are huge files. It's written in huge files. It's gonna take a lot of space. But the ASCII database are small text files, so it's very incredibly useful to just make small time intervals. Now for the parts section material for the tube. Before we go to the part card, we'll first create. It's easier for me, at least this way, to create the material card first, then the section, and then we'll assign them to the part. Here is the material card first. I'm gonna choose the 24 material card, which material piece was linear plasticity, usually used for steel materials. Just typing the density according to the unit system we chose, 210 gigapascal for the Young's modulus, Poisson's ratio about 0.3, and yield strength I think it was 0.2. With 200 megapascal, but we're using our unit system here, so it's in gigapascal, so it's 0.2. And for the hardening curve, either we can fill the cells, or we can define a curve. So here I'm going with the defining the curve method, and we can just type down the numbers from the slide. Be here in the following slide. Yeah, as you can see here, this is the curves, this versus plastic strain. Just start typing down the numbers. At 0 it's 0.0, then insert. Just keep going. 88 and insert, and the final one 0.5 and 0.43 insert. So if you click plot here, you'll see the curve. Sorry, I have to click accept first. Then you can press click on plot, and as you can see, the same curve you get for the stress versus the true plastic, the effective plastic strain. So I'm gonna name the card steel and accept, and done. Now I'm going to the section card. As you can see here, the curve and the material card are done, and then let's go to section card. Let's go to shell, and let's make the cross section, as we said, it's 1.5 millimeters, and the number of integration points, let's go with 5, which it's a good number because bending is governed by the stress distribution across the thickness, so more integration points capture the through thickness bending more accurately. So 5 is a good choice for the part that folds. Especially we have used element size of 5, so it's not very fine, right? So it doesn't take a lot of computational time. At the same time, it's not very coarse that it captures the folding of the tube. Then if we scroll to the part, we can navigate to section that we defined, section 1 for shell elements that we defined, and the material card is steel, and we just can click on accept, and done. We already did that in the beginning when we created for you the easiest way possible the geometry. Then I measured the surfaces, and as I said, I left one final step because I used a very trivial method, but just for you, if you as a beginner, it's easy. But I just dropped one final step to show you at the end. So we're moving on to contact card, which is very, very important step. Because the tube, as the tube crashes, the walls will fall over and come into contact with themselves. So without contact definition, those walls simply will pass through each other like ghosts, and the crash force comes out far too low. So the best card for this kind of application is contact automatic single surface, as you see here. No, not this one. It's contact automatic single surface, and the word single surface is the key. It means that the contact checks the part against itself, every surface against every other surface in the set, not just one body against a separate body. That's exactly what the self-folding tube needs. So we like the static friction and dynamic friction usually, and best would be 0.2 and 0.18 for steel material, and the rest would be just default to 0. And then accept, and done. Now we have to define the loading and the boundary conditions. The loading is the wall, the moving rigid wall, and the boundary conditions will be the anchor that hold the bottom of the tube fixed against the rigid wall. So the boundary conditions for the anchor or the fixed points of the tube is very easy, very straightforward. I like to use the create entity feature in LS-PrePost. It's a bit easier and just straightforward. We go to entity, then we go to boundary, create first, then go to boundary, and SPC, specific point constraints, or single point constraints. Then we can just choose the set of nodes we want to fix, which would be constrained in all 6 degrees of freedoms. As you can see, X, Y, and Z, and rotation around X, Y, and Z. This red cross means it's now fixed. and we can simply then click on apply and done. Now I'm going to create the rigid wall. I also like to use the create entity. For that, we just click on the rigid wall. We need to be moving and use moving with forces. And I'm going to use a mass of 500 kilos representing the car weight and initial velocity of 10 millimeters per millisecond. And we define the planar or the plane for the wall. As you can see here, if we modify it, we'll see it's the blue vector is heading downward, the normal vector, meaning is going in like in minus d. And we added the velocity in positive. What happened if the blue vector heading upwards? We just add a negative sign to the velocity, but I don't like to do that. Let's keep it downward, and just leave the velocity in positive value. I'm just showing you how it could be, because in the slides I think I added the velocity in negative value, just for you to understand what's going on here. Then when you scroll, navigate to the keywords of rigid wall, you'll find all the values we have, but don't forget to add the friction equal to 1, and we're gonna just add a node for additional visualization if we like to. Let's call it something odd like 5 lines. It's not created, so when you click on accept, it's not there, so we can like create it from scratch. It's easy. We just have to create new card, press add, and write down the odd name, which is 5 lines. Let's add the coordinates 25 in the center and about 205 and same distance of the rigid wall, and click accept and done. That's an additional feature. It's not necessary for you as a beginner to go through with it. Then we can now run using the solver. Write down I, which is short for input, equals the file name, and we can use the number of CPUs whatever you like or your computer can handle. It can run with one. That's a very light file. I actually did run it using just one, not necessarily 4. However, after running is finished, it doesn't mean that everything is right. You have to check everything. You have to check the force curve. You have to check the shape of the deformation of the tube. You have to check if everything is correct by your own eyes, based on your own expertise, even as a beginner. I'm going to show here something. See what happens? That's the step I left in the beginning. The tube doesn't fold properly. Even you as a beginner can see and can tell. I did that on purpose. I used a very trivial way to create the tube, which meshing each surface alone. However, because each surface overlaid with the other, they share common nodes. So if you use this method like me here, you have to merge these duplication of nodes so that the surface will come together as one. So we can just navigate to model, then check in duplication of nodes, show duplicate the nodes. As you can see the nodes, this is all duplicated, so we have to merge them, merge duplicated nodes and accept. Now we're gonna rerun it again. It's a bit more better, as you can see here. It's folding as you might expect it to see folding properly. You can then check the stresses, the strains. You can check just to make sure everything is properly and you didn't miss anything. You can check the force curve, like the plot of the rigid wall force from the RW force file. where it could be showing an initial peak at the first buckle forms, then a roughly steady folding plateau. The curve here is, you see, it's reversed because the wheel traveling from upwards to downward, the negative side. So we can just click on scale and remove the negative from the Y minimum and add negative or to the Y scale and just press apply. As you can see here, yeah, more or less it's well, I expect to see. And I also can check for the energy and the hourglass energy. As a rule of thumb, it should be the energy, internal energy should be the hourglass energy should be like less than 10% of the internal energy. And you can find the file, the file I built and the presentation in the description. I will leave the links for you. I will also leave the links for my store. Thank you.